Welcome back. In this video I'm going to carry on with the lithium-ion cell capacity checker, and I think this is series 17 now. So one of the problems with this thing is that the voltage that it senses isn't accurate. So just to show you, it says voltage 4.37, and that almost certainly is not right, because lithium-ion cells should never be that voltage. So it's actually 4.07, so it's quite a lot off, and we need to sort that out. And there's a very simple solution. It's not entirely accurate, but it will get us about 5%, 5% plus minus, which should be okay for this. And that's just to change the volts per count parameter that I've got in the sketch. But anyway, let's check what the voltage is of the actual Arduino via this USB cable I've got to the PC. Let's just see what the voltage is to start with. So ground and 5 volts. It is nothing, surely that's not right. 4.65, okay, 4.65 volts. And we're going to use that as a reference, so 4.65. Okay, so this voltage per point here, or voltage per count, I've got as the standard 5 volts. So 5 volts divided by 1024 equals 4.8 millivolts. Well, that's of course not right in this situation. So this is a very nasty way of doing it, but you know, whatever. 4.65 divided by 1024 will give us the amount of voltage per count from the ADC, and it is 4.6 or 4.54 millivolts. So I'll paste that in there. In fact, there's another way of doing this as well. Let's do it properly. So let's say const, well, not properly, but you know what I mean. Device voltage equals 4.65 volts, and then voltage per point equals the voltage divided by 1024. And that's a better way of doing it. So if you copy this sketch to yours and you make this thing, all you have to do is change this. Now this could potentially change for every different charger that you put in. I'm not 100% sure. Like I said, it's a bit of a a cheap, rubbish way of doing it, but anyway, it'll do for now. So upload, and let's see what happens. Okay, so it says hello, insert cell now, press run ready. It says the voltage is 4.06. Well, let's just try it out to make sure. 4.06, absolutely perfect. So that's that problem sorted out and solved. So if we use a different power supply, it might be the case that this will change. I'm not 100% sure. Okay, so we've dealt with that, but there's something we need to look into in a bit more depth, and that is so it's saying 3.82, which is right, but what about the voltage when it drains? And that's what we need to look into. So I'll press go, and straight away it drops to 3.35. But you can see the multimeter saying something different. It's saying 3.38, and that's saying 3.23. So one of them is right and one of them is wrong, and I think the multimeter will probably be right. So what it means is the Arduino is, at the moment, it's 30 millivolts out, and then now it's not out, now it's fine. It's fluctuating. It can be up to 200 millivolts out, so there's still a problem there, but at the moment it's not a huge deal. We're getting there, but it just needs a bit more attention. Another thing I want to deal with in this video, in fact right now, is that it says here 0 minutes 41 seconds drain time, which might be right because this cell's probably dead, but 0 milliamp hour, it works off hours or minutes, but I've decided that I don't want to do that. I want it to work off seconds, so I'll sort that out now. So I want to readdress this area here. I've got duration millis equals drain stop, take away drain start, so that's the amount of milliseconds. Then here I divide it by 1000 to get seconds, and that's a great start. Then over here I get minutes, and then seconds with the minutes already taken out, and that's for this little area here. But over here, where it's got the milliamp hour, this is the bit that needs to be changed. So let's rewrite this thing. So we're going to need, well, the amount of time to start with. So duration in seconds, duration total seconds. We need to divide that by 3,600 to find out how many hours, because this is milliamp hour. And then we need to multiply that by the average amperage, so average amperage, and hopefully that will work. Let's just double check it. So the amount of seconds, so if that's 3,600, divide that by 3,600, so that's 1, and then multiply by the average amperage. So if the average is 1, then that would be, right, well let's just double check that again. So 3,600 divided by 3,600, if it was an hour, would be 1, multiplied by, say, 1 amp, so it would be 1 amp hour. And now, yeah, we need to multiply it again to get milliamp hour. So multiply by 1,000, is that right? I think that's right. So let's upload it and see what happens. Okay, so I've got a cell. It says 2,000 milliamp hour, and it's not fully charged. It's like 4.2 volts, but it was fully charged. I think it's like self-drained or something. It's now 4.04 volts, but we'll check it in here anyway. Really, to be able to check the capacity, of course, you need to be fully charged, but I'm just testing. So it says 4.05 volts. Let's go ahead, discharge it and see what happens. So straight away it drops. I think I'll just check the drop across the resistor just to make sure. Yeah, check the drop. And it is, if I can keep this thing still, 1,320 or something like that. 1,320, so yeah, the amperage seems to be about right. Okay, so we're about 10 or 11 minutes into it, and let's do some checks. So first of all, we'll check the voltage. So it's saying 3.57, and let's just check this for ourselves. Okay, this is saying 3.74, so there's a problem there. Yep, there's a problem there. And well, actually, let me just check from there to the Arduino ground, and let's see if that makes any difference. Arduino ground, 3.45. Yeah, okay. I'm just trying to do that so the camera can see it. Ground, 3.55. That's what this is saying here, but the problem is, from the cell, it's actually 3.7, so we have a problem, but we'll deal with that anyway. We'll deal with that at another point. But anyway, that was one check that I wanted to do. And the other check I want to do is the heat. So if things get extremely hot here, we could end up burning things. And the things that are likely to get hot are the transistors and, of course, this thing here. So I suppose I'll start with just a touch and see if it feels okay. That feels quite hot, but not anything. It's not, you know. There you go, 43, 44 degrees. That's okay. And the transistors, whoa, they feel very, very hot. So we might have to change these things. Let's see what temperature they are. 57. And this one, 80 degrees centigrade, something like that. Yeah, 80. So that's too hot. They're not supposed to be running at that temperature. So what I'll probably do, I'll probably get a MOSFET or something instead. And you can do it with transistors, but I'll probably get a MOSFET. And I think the reason why they're getting so hot is because they're not fully opening. I can't remember the exact word now, but they're not fully opening, and therefore there's quite a lot of resistance within them. So I'll have to research that a bit more. But there we go. I'll let this test go anyway. This will be the first test, the first proper test anyway. And we'll look at the results and go from there. Okay, it's done. So let's have a look. The average amount of amps flowing through the resistor was, well, through the circuit was 1.32 amps. And the thing took 73 minutes and 42 seconds, and it's saying that the milliamp hour is 1324. And that's not right. It's definitely not right, because if it was 1.32 amps and it's for 1 hour, it will be, 1.3 amp hour. And it's saying it was over 73 minutes, so it's definitely not right. So we'll need to address that. So there's a very weird problem here to start with. I'll just go and get the figures. 73 minutes 42 seconds. 73 minutes and 42. Oops, 73 minutes and 42 seconds. So let's convert this into seconds to start with, because I'm sure this isn't right. So that multiplied by 60 to get seconds, and plus that, so equals, you don't actually have to use sum, but I will anyway. So total amount of seconds, 4,422. 4422. Okay, so that's the amount of seconds. And what's the amount of, let's see, average amps? 1.32. 1.32 is the average amount of amps. So, right, so let's work this out then. So, what do we do? Well, let's make this smaller to start with. Okay, and let's follow the code that I've got here. So we've got the duration total seconds. So that's 4,000 and, let's have a look, 4,422 divided by 3,600. That's obviously to get seconds into hours. Then we multiply that by the average amperage, which is this, and I'll close the brackets, and then multiply that by 1,000. And it's already an int, but okay, we'll put int on anyway. But it's already an int, but just for completeness, 1,621. So how's that even possible? It's showing 1324 milliamps. How the hell is that even possible? I've worked out what's going on. I mean, the calculation, the formula was right, and I was following along with the calculator, and somehow doing exactly the same calculation, the Arduino was coming up with different results. And I was thinking, in the end, I was thinking, what the hell is going on? If Arduino can't calculate, then we're going to have big problems. But anyway, I found out what the problem was just by messing about and simplifying. It's usually the way I diagnose. And the problem is, when you divide integers in Arduino, it can't deal with it, and I don't know exactly why, but whatever. So for example, if I was to get 60 seconds, like this bit here, 60 seconds, and divide by 3,600, the calculator's got two integers and made it into a float here. It thinks, oh right, well the answer's not an integer, it's a float, so display it likewise. But with Arduino, even though you write here float, it still doesn't understand for some reason. For some reason, it does the division and then makes it back into an integer. I don't know why it does that, and then it puts it into float. So it's just not clever enough to know that the answer is a float. So whatever. But anyway, the way to fix it is by casting both values as float, so it knows, oh right, whatever the calculation is, we want it to express the answer as a float. So whatever, that works. So I've put that in there, and I've done the rest of the calculation and displayed it, and now it works. And I'm just going to show you now anyway. 3.8 volts, go. So, we'll give it 30 seconds or so, and then we'll work out, you know, the calculation and see what happens. And while we wait 30 seconds, I suppose I'll show you what I'm going to do next. I've got this buzzer. I'm going to put the buzzer in so that when the thing's finished, it's going to buzz, as well as the LED. And, well, that's one thing. Time's up. So 30 seconds. So it's saying the average is 1.17 amps over 33 seconds, and it's saying that that's 10 milliamp hour. Alright, so 1.17 for 33 seconds. So to start with, total seconds, 33 seconds divided by 3,600 is that, and then the amount of hours, which that is, multiplied by whatever the amperage was, 1.17 equals that, and then multiply that by 1,000 equals 10.72. So I suppose we could round that up to 11 really, but it doesn't matter. For the sake of a milliamp hour, it doesn't really matter. So 10 milliamp hour is correct, and it's coming up with it okay now. So we've resolved quite a lot in this video, and we're really getting there now. And there's another thing I'm going to do just before I finish. Here, I'm going to change this to average milliamps is throughout the drain. So average milliamps, average. So we want the average multiplied by 1,000 to get milliamps, and then this is going to say milliamp. And I'd almost forgot, we need that to be an int as well. We don't want to see decimals when it comes to that thing. Okay, so let's have a look over this thing, and let's see where we are at the moment. So it says the welcome thing, insert cell now. So we'll press that, and it says the voltage, and press the start. So we'll press the start button. And it says the voltage, the amperage, and the duration. So we can actually terminate this thing early. If I press this button now, it'll terminate it. So we might as well terminate it. 14, 15, and it says the average in milliamp, in milliamps. So the average is 1,182 milliamps. That's per reading. And then it says 0 minutes 16 seconds duration, and then it says the capacity, which is 5 milliamp hour. So that's assuming that the battery has been, well, the cell has been draining for you know, its full charge, so 4.2 volts to 3 volts, which is of course not the case here because I terminated it early. But the next thing I'll probably do is do a full discharge, well, a full charge and a full discharge of a cell, and see how it's looking. But anyway, that's that, and I'm happy, so I'll press the next button there to restart. I'm very happy up to now. So there's a couple of observations though. First of all, I think it needs a buzzer, because if I'm sat at my desk and you know, it's drained and the LED shows, I might not see the LED, or I might forget or whatever, but something audible is more likely to get my attention. So there's that. I think it needs a buzzer. The second thing is that I noticed before, as I think I might have shown you, these transistors get very, very hot. I think they get to about, I think typically they're about 60 degrees or something like that, but really that's too hot. I prefer them to be a lot colder than that. And also that will mess with the circuit, because there's obviously heat being dissipated from those things, and there's a cost to that, whether that's from the cell or whether it's from here. I'm not 100% sure, but there's a cost for it. So obviously we don't want it to be in this side of the circuit, because then it's going to skew our results. So yeah, we need to change that. So I've got one of these. Well, there's potentially a lot of different things we could use, but this is an IRLZ 44N, and this is a MOSFET, it's not a transistor, so I might end up using this, but I'm not 100% yet. I've got lots of different things to choose from, so yeah, I don't know. And the other thing is that at some point soon I'm going to have to look at making a circuit board or something for this, because these wires are a pain, and when the wires have gone it will affect the circuit differently. I mean, there's actually a voltage drop across these wires, and when the wires are gone it'll be a lot better. So there you go, that's today's video done, and I hope you enjoyed it, and as usual, thanks for watching. Bye.